Hello students, in this class, hash based upon the same. So now let's get into our topic. Here now let us see about the cipher block chaining. Cipher block chaining, how we are going to perform this cipher block chaining based upon a hash function. Okay. Here the number of proposals that have been made for the hash functions based on using a cipher block chaining. So after proposing the number of proposals, that how we can perform this hash based functions. In the previous classes we have discussed about the hash functions also. So by using this hash functions, how we are going to perform a cipher block chaining technique. Now let us see. But without using a secret key. Here why you are using the secret key is just for the encryption purpose. So without using the secret key, how we are going to perform this cipher block chaining, that is based upon the hash functions. Now let us see. So here one of the first such proposal was that of Rabin. He proposed this proposal. Here we will divide the message M into fixed blocks. See, suppose this is a for example, if you have taken the message called hi, hello, how are you, just like that, some length of the message, we are going to first of all here in this process what we are doing is we are going to divide that message into fixed blocks, that is M1, M2 and so on, like that. Here we can use this symmetric encryption system such as data encryption standard algorithm to compute the hash code. Here what are the encryption standards that we are using here is data encryption standard just to compute the hash code. Okay. We can the hash code that is generated we can denote with Z. So we can take this one H0 as the initial value and Hi is equal to encryption, that is E is encryption, Mi is the number of blocks that we have divided, and Hi minus 1 is up to initial value and Hi minus 1 is the final value. So up to final value we are going to perform the encryption. Just like that. Suppose if this is the suppose we are having some fixed length message, we are going to divide that fixed length message into several blocks. Okay, for that fixed length message, this is Mi is up to this many blocks we have to perform, and up to this much code we have to perform the up to this much values we are going up to this final value we are going to perform this, where G is the hash code that we are going to generate here. Okay. So from this we can say that this is similar to CBC technique, means cipher block chaining technique. CBC is a cipher block chaining technique. So, but in this case there is no secret key. Here we are not having any secret key to generate. As with any hash code, the scheme is to subject to the birthday attack, such that birthday attack means whenever the code we have generated, that is the first day for that code. So we can say that one as a birthday. Okay, birthday attack. And if the encryption algorithm is here, we have already said that the encryption algorithm that we are going to use is data encryption algorithm. So from this we can generate up to a 64-bit hash code, and it is produced on a system is vulnerable. So furthermore, another version of the birthday attack can be used, even if the opponent who is taking that particular message has to access only one message, and it is a valid signature and cannot obtain multiple signings. So the person going to take that, the person who are going to take that one is a, even if he have his opponent has access to do that, but he opponent also has to access that once, at least once. That is also by using the signature itself. Without using the signature, he can't able to access the multiple signings. Okay, here it is a scenario that we are here we have to assume that the opponent intercepts a message with a signature in the form of an encrypted hash code, and that the encryption hash code has m bits long. So from this, how we can say that this is similar to the cipher block chaining technique, and here the encryption algorithm that we are going to use the data encryption standard algorithm. And we can say if it is in the message that we have generated in that day itself, it is attacked, then we can say it as a birthday attack. And if the encryption algorithm is a if you are using the data encryption standard algorithm, then the limit for that is 64-bit hash code that is produced, that is the output. So the opponent who is going to receive that particular message, he has to he has a technique called, he has to do the signature to receive that particular message, and he should not allow the multiple signings. Okay, multiple signing should not be allowed here. So this is how we are going to produce this 64-bit hash code. If you have taken this example called, if the sender is sending some 2 to 3 pages of message, and the receiver has to receive that message, but without any illegal use of data, you have to, without any proper authentication, we should the third party person should not get that data. So here the in the cipher block chaining technique that is based upon the hash function, what is the process that we are going to do is, the message is divided into m blocks. So further the encryption is on that the encryption is performed here, and for that you have to, for that we are using the data encryption standard technique, and without using the secret key we are going to generate this one. So here we are assuming that the opponent will not intercept any message, will intercept a message with some signature in the form of encrypted hash code, and that the encryption hash code is m bits long. Okay, see how we are going to do here. First of all, we have to use the algorithm defined at the beginning of the subsection to calculate the unencrypted hash code. See, the message which is not encrypted message, we can say that one as an unencrypted message. So for that unencrypted message, we are going to generate the hash code. Okay, for that first, this is the first step that we are going to follow. Okay, then next what we have, the next step what we are going to follow is, we have to construct any desired message in the form of q1, q2, q3, just like that up to qn. Okay, next one, we have to compute, that is we have to perform the q1 q2 means we have to divide that message into blocks. No, that is the second step. First step is we have to use the, what is the algorithm that we are going to define, that you have to use first, and you have to calculate the unencrypted hash code. Unencrypted hash code means the message which is not encrypted, we can say it as an unencrypted hash code. So from this we can construct any desired message from q1, q2 and so on, q1 minus 2. So from that message we are going to divide this one. Next one, here we are going to compute this message hi to e of qi comma hi minus 1 for I to n minus 2. Okay, this is we are going to ante enti ikkada, this is the message that we are going to use here, and this is the number of blocks, this is the number of blocks that we have, sorry, this is the number of blocks we have divided, and this is up to this final value we are going to, up to this final value we are going to compute this message, and this is the encryption that we are going to perform here. Okay, here the from I, for I is equal for 1 to n minus 2, up to I and n minus 2. Okay, here we are going to generate 2m by 2 random blocks. That is how many blocks that we are going to divide, that is randomly we are going to provide here, and for each block x compute e of x comma n. For each and every block we have to perform this type of encryption. Okay, here see and next we are going to perform is we can generate an additional random blocks if the block that is that we have divided block, the blocks that we are going to divide is not sufficient, then we can generate the additional random blocks for each block, and we can compute that where d is the decryption. Okay, then we can compute that message, that block with decryption. Here we have already said d is the decryption function corresponding to e. So based upon this paradox, with high probability there will be x and y such that, see, if you are confused with this standard, this is not nothing difficult. So d is a decryption that we are using. So y is the message that we are going to keep here. G is the number of blocks that we are going to divide here. So just like that we can remember that one. So here E is the encryption that we are going to apply, and here we can take this X as a number of blocks. So here X is the number of blocks at the sender side. Just like that we have, why you have to perform decryption at the receiver side. Whatever the sender that have send the మనం సెండర్ సైడ్ నుంచి ఎన్క్రిప్షన్ పర్ఫామ్ చేసినప్పుడు, ఎన్క్రిప్షన్ అంటే ఏంటి, మెసేజ్ అనేది ఒక డిఫరెంట్ లాంగ్వేజ్లో మనం దాన్ని కన్వర్ట్ చేస్తున్నాం. ఎందుకు డిఫరెంట్, ఈ మెసేజ్ ఎందుకు డిఫరెంట్ లాంగ్వేజ్లో కన్వర్ట్ చేయాల్సి వస్తుంది అంటే, why you are going to convert, just to provide the security that third party person should not allow to access the particular type of data. Okay, so at this sender side we are going to encryption. This is the receiver side, that here that particular person is going to decrypt that particular data. Okay, up to here clear. Here this is the final value, up to this blocks, up to this final value we are going to perform the encryption. Okay, next one, here from the message q1 q2 a and qn minus 2, x comma y is a message has the hash code G, and therefore it can be used within the encrypted signature. Okay, so from this message whatever the blocks that we have divided, q1 q2 and so on, q1 minus 2, x comma y, this is a message has a hash code. From this message we can generate a hash code G. The message after generating that the whatever the message that we can collect, that is we can say that one is the hash code, we can represent it as a G. So and therefore it can be used with the encrypted signature. So at the time of whenever you are going to provide the encryption signature, at that time you can use that one. Okay, see, this is a form of attack as meet in the middle attack. So the number of researchers have proposed refinement. So at the middle of the time, if somebody has if something has tried to attack that one, then how we are going to reach that and research that, and how we are going to again how we are going to protect our particular data. And this is the form of attack known as meet in the middle attack. And so the number of researchers have proposed the refinements intended to strengthen the basic blockchaining. So for example, if you have described the variation, see, this is up to this is the XOR operation. We have already know that this is the encryption that we have performed. For that we are going to add this particular kind of thing again. Why? Because if we meet in the middle, if sometimes if they have attacked, if you find that somebody is going to attack for that particular data, then the process that we are going to apply here is, here we are going to perform the XOR operation. With this particular example, hi minus 1 is up to this final value, where I is from 1 to whatever the blocks that we have divided. Suppose we have divided to 10 blocks, that is here the I value is 10. So 10 minus 1, that is up to h9 we can. This is just an example for example I said. Okay, this is how we are going to describe the variation. Another variation also we can propose is just like this is just for simply reversing the technique. Here just like this also we can follow up to this is the final value, and this is number of blocks that we have divided, and for that we are going to add the number of blocks up to number of final values, or number of blocks also we can add just to protect from the attackers, just to take out from the meet in the middle attack. Okay, this is how a number of researchers have proposed the refinement intended to strengthen the basic block chaining technique. Okay, and this is a secure hash algorithm. This is about the secure hash algorithm. In recent years, most widely used hash function has been the secure hash algorithm. So here in this secure hash algorithm, the main intention of the secure hash algorithm is the secure hash algorithm has to provide the security for the hash function. That is basically why it is using for this is in blockchaining technique. In the now itself we have discussed in the blockchaining technique, we have used this hash function. Sorry, we have used that hash function. So instead of using that one, instead of using anything, you can take this one as a, if you have used this secure hash algorithm, then it will be very easy for the person who is going to encrypt the data. Okay, so in recent years the most widely used hash function has been the secure hash algorithm. Okay, from the years itself we are going to use this, we are using this secure hash algorithm. So because virtually each every other widely used hash function had been found to have the substantial cryptanalytic weakness. So secure hash algorithm was more or less that last remaining standardized hash algorithm by 2005. So secured hash algorithm was developed by the National Institute of Standards and Technology and published as a federal information processing. So when weaknesses were discovered in the secured hash algorithm, now known as secured hash algorithm, a revised version was issued as uh, first institute of FIPS. This is a standard, FIPS standard. So FIPS 181 is a standard in 1995. So based upon this standard, the secured hash algorithm has been introduced. Why it has introduced is why it is a widely used hash function. Why it has introduced is to use to for the substantial cryptanalytic weakness. Okay. Uh, Secured hash algorithm was more or less last remaining standardized hash algorithm by 2000. Up to 2005 it's also it is a standard algorithm and was developed by the we have already know it was already developed by the National Institute of Standards and Technology and published as a federal information processing standard. So when the weaknesses were discovered in the secured hash algorithm now known as SHA0. We are providing the versions now. Now it is called as SHA0, and we are having another version called SHA1. Just like that, we are going to increasing that versions. Okay. So SHA produces a hash value of 160 bits. So in 2002, National Institute of NIST means National Institute of Standard Technology produced a revised version. So up to secured hash algorithm is this is first version. This many versions has released SHA1, SHA224. SHA means security hash algorithm. Okay, SHA1, SHA224, SHA256, SHA384, SHA512, just like that. Okay. This is a message size. Here, this is a message digest size. This is a message size. This is a block size. This is a word size, and this is a number of steps. That is in SHA1. The message digest size is 160, and the message size is up to 2 power 64. Until this number, we can use the message. That is, we can use this length of message. We are having to store that message. We are having the block size of 512 and each word having the size of 32, and the number of steps that we are going to follow is 80 here. Okay, here in SHA 224, here the message digest size is here up to when compared with this, here the message digest size has increased, and when compared with this, here also the message digest size has increased, and when compared with this, here increased in SHA 384 the message digest size has increased, and when compared with this one, here the message digest size has increased. So here in all the SHA parameters the message size is same. Okay, here in SHA1, SHA224, SHA256 the block size is 512, but in SHA384, SHA512 the block size is 1024. Okay, here in SHA1 and SHA224 the word size is, sorry, in SHA1, SHA224 and SHA256 the word size is 32, 32, 32 itself, no change. But in SHA384 and SHA512 the word size is 64 and 64. Okay. Here in SHA1 the number of steps is 80, and in SHA 224 the number of steps is 64, and in SHA 256 the number of steps is 64, and in SHA 384 the number of steps is 80, and in SHA 512 the number of steps is 80. Okay. Here these are the all sizes are measured. Here the all sizes are measured in bits itself. Okay. Next one. So if you have, how we are going to generate this message in secured hash algorithm, this is block size of 512. Okay. If you have observed this, see, this is the message that we are going to generate here. This message is divided into blocks. This is first block, this is second block, and so on, mn blocks. Okay. For this, from this we are going to generate the some fixed code. For that we have performed an XOR operation up to H0, H1, H2, the up to Hn we are going to perform the XOR operation. Okay. This is the message digest function, message digest generation using the secured hash algorithm. See, this is the 128 bits. So up to 128 bits we can generate that message. So here each block is divided into 1024 bits. For that we have generated, after performing encryption and after and all those, we have generated a code. Okay, the code that we have generated, we can say it as a hash code. For that hash code we are going to add these values, key values. Okay, so h0, h1, this is initial value, this is second value, up to final values. We are going to performing the XOR operation here. Okay. Next one, here in step 1, what the process that we are going to do is, here the message is padded so that its length is congruent to 896 and modulo 1024. A padding is always added even if the message is already desired length. Thus the number of padding bits in the range of 1 to 1024. The padding consists of single 1 bit followed by the necessary number of 0 bits. So this is append length, so that the a block of 128 bits is appended to the message. This block is treated as unsigned 128 bit integer. So we can say it as the most significant byte first. So, and it contains a length of the original message before padding. Before padding, it is having the it contains the length of the original message before padding. The outcome of first two steps yields a message that an integer multiple of 1024 bits in the length. So in the next figure we can show that the expanded message, and it is represented as a sequence of 1024 bit blocks, that is m1, m2, and so on mn, so that the total length of the expanded message is n into 1024 bits. So here we can process the message in 1024 bit 128 word blocks. So here the heart of the algorithm is a module that consists of 80 rounds. This module is labeled F in figure 11.8, and the logic is illustrated in figure 11.9. Now let us see this figure. See, this is a scheduled message. Here this is a round 0. Okay, this is a round 0. This is a first block. This is first block. This is ith block. Just like that, up to 79 blocks of suppose we have designed it is we have divided into 80 blocks. Okay, this is first round. This is round T, and this is round 79. Just like that, up to this one A, B, C, D, that we have divided into the bits. Here that is 64. Here that is a key k0, k1 up to k19, k79 we have generated a key. So here after scheduling this message, okay, after scheduling this message, we automatically it is first the round 0 is performed, and after that round 1, round 2, round 3 up to round t, and up to that round 79 we have performed. After that, after performing all those rounds, here for each and every round we have to calculate the for each and every round we have to calculate the XOR operation, that is up to HI. So here we are going to process a single 1024 bit block. Here after all n1024 bit blocks have been processed, the output of the nth stage is the 512 bit message digest. So from this, we can summarize the behavior of SHF 512 as follows. See, this is how we can summarize. So H0 is the initial value. So we can define it as a 4. So HI is a sum up to some 64. 64 is a bit. Okay, 64 bits we are going to divide. HI minus 1 is the final value, and this is the message A B C D E F G H I is the message that we are going to divide. We have applied here, and MD where MD is the final message digest value. Okay, that is HN. Okay. Here this one is the initial value of the 1V is the initial value, IV is the 4, just like for Roman 4 we have right. So where 1V is the initial value, okay, IV is the initial value at ABCDEFGH buffer, where we have defined it in the step 3. So ABCDEFGH is the output last round of the processing ith message of the block. N is the number of blocks in the message including padding and the length fields, and sum 64 is the addition modulo 2 power 64 performed separately on each word of the pair of inputs, and MD is the final message to digest value. Okay, up to we have discussed in this class, we have discussed cipher block chaining based upon the hash function, and next one is secured hash algorithm. Okay,